Thanks for tuning in to the training topic today. We're going to be talking about one CHP practice question and a case study that pertains to medical health physics. I'm Lieutenant Jeff Caudill. I'm a Medical Service Corps Radiation Health Officer. I'm currently stationed at the U.S. Navy Hospital in Yokosuka, Japan. My primary job is the Radiation Safety Officer, but I also serve as the Radiology Department Head and the Laser System Safety Officer. Let's get started by talking about one of the questions from the 1997 American Board of Health Physics exam. When we get started looking at this question, you always start by looking at what's given in the problem. So what they give you primarily on this screen is the conditions and results of survey measurements. So there's a physicist who was doing a routine annual survey on a general purpose X-ray machine. And here's the setup that the physicist used and the radiation exposure rates that were produced as a result. The first thing they tell you is that the X-ray beam was oriented vertically and the central axis of the beam was normal to the patient table, which is how you would set it up for a patient. It's good they told you that. Next, they told you where the ionization chamber was located that recorded the radiation measurements. Next, they tell you how deep below the table the image receptor is when it's in the cassette holder. After that, they tell you the source to image receptor distance when the radiation measurements were being recorded. And then after that, they tell you the technique factors that were used to record each of the radiation measurements. So they kept the mass constant. The mass is a current time product of what is being applied to the X-ray tube head. And then they also record the changes in kVp, which is the applied voltage to the X-ray tube head. Some additional information they provide is the source to image distance for 2 diagnostic imaging exams that were done on various patients. So you're going to have to keep those in mind because they're not provided in the problem. You actually have to come back and reference it when you reference the radiation exposure rates that were recorded during this survey. Here's a quick explanation of the survey data collection and how it was set up. I'm using an actual example from a physics test that I did on one of my X-ray rooms at my hospital. So what we're trying to get to is the source to detector distance, but as you can see on the screen, some of the values that they gave you in the problem are the source to image distance being 100 centimeters. That's the distance from the focal spot where the electrons are hitting the spinning tungsten target inside the X-ray tube head, from the focal spot to the image receptor, which is located below the table. So the distance below the table is 7 centimeters, and this can come from a tape measure, or you can find it from the technical manual, which is preferred. It's more accurate. And then the detector stand is 30 centimeters. That's the detector stand or detector distance. The stand elevates the solid state detector from any flat surface, and it eliminates or minimizes backscatter. Now, I used a solid state detector for my test. The problem uses an ionization chamber, but in the end, it doesn't matter because you have a recorded radiation measurement. So to calculate your source to detector distance, you take your source to image distance, subtract your image receptor depth below the table and your detector stand distance, and you come up with 63 centimeters after you substitute your values. So as a side note, the SID can be established by several different methods. Large X-ray rooms with the overhead mechanisms have indentations to mark 40 inches or 72 inches. The tube heads always have an installed tape measure, so you can use it at any angle you want and take the image however you want from any angle. And then there's a manual tape measure, like I do when I do my testing. I like to take it manually. And then there's a digital indication of SID on tube heads for newer units. Part I starts off with giving us the given information specific to this part of the problem. They give us a kVp and mass, which are technique factors used for this patient examination, which is an AP abdominal exam. The patient thickness is 10 inches. And then from the initial data that we'd covered earlier, we're given a detector distance or height above the table of 4 inches, an image receptor distance below the table of 3 inches, and the survey measurements that we took with the radiation meter gave us a mass of 10, and at 75 kVp, which is what this exam uses, they recorded 112 milliroentgen. Also looking at the source to image distance specific for an AP abdominal exam, you know that it's 40 inches. Now, if you look at the second to last sentence, it says the screen film speed is 250 and a 10-to-1 grid is used. We can tell this is erroneous or not useful information because the radiation survey measurements that were recorded by the physicists were also performed with the screen film and grid at the 10-to-1 grid ratio. So it can be assumed that the parameters are negligible and they don't matter, so we're not going to take that into account in our calculations. Our goal is to take a survey measurement that we took with our radiation detector and transform that using the inverse square law to an entrance skin exposure at the patient's skin. So using our detector parameters, we have a detector stand or height of 4 inches, a receptor distance below the table of 3 inches, and an SID of 34 inches. That can be used to calculate a source to detector distance. With our patient on the table, we have a patient thickness of 10 inches with the same receptor depth of 3 inches, but instead this patient exam set up for 40 inches. So with those variables, we can calculate the source to skin distance. Using the inverse square law, we're going to be able to take the exposure that we measured, using the inverse square law, and transform or convert that into an entrance skin exposure at the patient's surface of the skin. Another factor we need to take into account when converting from our detector exposure to the patient exposure at their skin is the mass between the two radiation exposures. So recall that 1 amp equals 1 coulomb per second. By looking at the simple relationship, we can infer that by increasing either current or time, we're going to get a directly proportional increase to the radiation produced. If you look at the bottom left graph, we can see the relationship between X-ray spectrum taken at a regular setting for mass, and you multiply that by 2 and 3. The end result is the same spectrum, simply elevated in height, which is the relative photons produced during each exposure. So we know that our survey technique was 10 mass, and our patient technique for the actual patient examination was 60 mass. So to determine our patient exposure, it's merely a product of the detector exposure and the relationship between the patient and survey techniques that were chosen. We're finally at the point where we can calculate our final answer. First, we'll calculate our source to skin distance and source to detector distance. So your source to skin distance is equal to the source to image distance of the patient exam minus the patient thickness minus the receptor depth. So 40 inches minus 10 inches minus 3 inches equals 27 inches. The source to detector distance is equal to the source to image distance of the survey minus your detector distance minus your receptor depth below the table. So that equals 34 inches minus 4 inches minus 3 inches, which is 27 inches. Now to calculate our entrance skin exposure. Your entrance skin exposure is equal to your radiation measured times the relationship between your mass settings of your AP abdominal exam and your survey technique settings times the square of your source to detector distance divided by your source to skin distance, which is an application of the inverse square law that we already learned about. After substituting our values into the equation, we're left with 672 milliroentgen. We're in luck with part B because it's basically the same question as part A, just with a couple changes to see if they can throw you through the ringer a little bit. So they tell you that it's a PHS exam, and for this exam they have technique settings of 115 kVp and 5 mass. They also tell you to assume that the distance from the chessboard surface to the cassette can is 0, so that's basically telling you that your receptor distance behind the surface is 0 inches. And then they also tell you that the patient thickness is 10 inches. Now, from the given information from the initial survey data, we already know that the detector distance is 4 inches, that the survey techniques were all taken at 10 mass, and using the 115 kVp setting, we know that the exposure measured is 264 milliroentgen. Now, this is a different diagnostic exam. It's a PHS exam, so we have to get that different source to image distance, which is 72 inches. And last but not least, I included the same assumption, which is the screen, film, speed, and grid is erroneous and not useful information. We don't need to use that in solving this problem. Moving right into the solution, we're ready to calculate our entrance skin exposure after we calculate our source to skin and source to detector distances. Our source to skin distance is equal to the source to image distance of the patient minus the thickness of our patient minus the receptor depth below the table or the wall bucky.
So that equals 72 inches minus 10 inches minus 0 inches, which equals 62 inches. Our source to detector distance is equal to the source to image distance of our survey measurement minus our detector stand minus our image receptor depth below the table, which is equal to 34 inches minus 4 inches minus 3 inches. It's important to remember that 3 inches was from our initial survey data when they had the image receptor below the table, not the wall. All that equals 27 inches. So calculating our entrance skin exposure, we have that equal to our exposure measured times the relationship between our PA chest exam mass and our survey measurement mass times the square of our source to detector distance divided by our source to skin distance. After we substitute in our values and solve, we're left with 25 milliroentgen entrance skin exposure for the patient. Part C asks us to recommend 2 procedural changes which could reduce the entrance skin exposure to the patient. I'm going to list 5, but you only need 2, so keep that in mind. The first one, decrease mass. This decreases the image quality, which becomes a problem if the image is already optimal. 2, decreasing KVP would also decrease the entrance skin exposure and image quality, which is a problem if it's already optimal image. But between the two, it's important to know that the exposure is proportional to the KVP squared, so it's not directly proportional. Number 3, you can switch to digital radiography. The modality they're referencing in this question is an old modality. They're either talking about computed radiography or old film, which you actually have to develop. Switching to digital radiography can have an up to 50% decrease in entrance skin exposure. You can use image intensifying screens. These would increase image quality, which would allow you to decrease your exposure techniques, therefore decreasing entrance skin exposure. And then finally, with number 5, increasing the film speed. If you increase the screen film speeds, it increases the sensitivity of the phosphor, which means less X-ray radiation is required to produce a given optical density.
Part D of this problem starts off by saying you have a technologist standing 1 meter away from a patient during an AP abdominal exam, and that technologist is not wearing a lead apron, not standing behind any kind of control room wall, so there's no attenuation of the scattered radiation. The question wants you to figure out what is the technologist's exposure, but they give you very little information. So you need to know that there's some sort of thumb rule that you need to know in the back of your brain to be able to solve this problem. The solutions from the ABHP website use one method, and I'm going to teach you a different method, but they both end in the same result because they're basically the same thumb rule. So for the given information, what we're going to do is say the entrance skin exposure to the patient is 672 milliroentgen, which was taken from Part A. So as long as you say you're taking that information from Part A, it really doesn't matter what your final answer is, as long as you do it the correct way, because you're stating your assumption of where you got your entrance skin exposure. The technologist distance is 1 meter, and from the ABHP solutions, they use a scattered exposure at 90 degrees factor, an R factor, of 1 times 10 to the minus 3 meters squared.
Now, what happens when these X-rays enter the body? The primary method of interaction of these X-rays with matter is Compton scattering due to their energy range. These photons come in, interact with the orbital electrons, and these electrons receive some of the photon's kinetic energy, which frees it from orbit. The photon then has a decreased energy and longer wavelength, while the electron travels on until it interacts with other matter. The X-rays can be scattered from 0 to 180 degrees, but what we're concerned about is 90 degrees scattered radiation. I say that because the patient is laying down for this exam, laying on the table. So if you're standing anywhere in the room at 1 meter, the scatter radiation is going to be at 90 degrees while the X-ray is coming in perpendicular to the table. So using our equation on the right, we can calculate the energy of the scattered X-ray. After we put in 90 degrees for our angle, we come up with an energy of 65.4 keV, which is a decrease from our original energy of 75 keV. Another factor the solution doesn't take into account is the relative probability of the scattering angle. So the image on the screen is from a medical physics textbook, and they have 3 different energies of these probabilities. 80 keV is pretty close to 75 keV. So we'll use that one. And the scattering angle of 90 degrees brings us over to about an 80 to 80% relative probability.
One thing that came to mind when I was reading the problem was the R value of 1 times 10 to the minus third meters squared. That reminded me of a statement I read from the American Association of Physicists in Medicine report number 58, Managing the Use of Fluoroscopy in Medical Institutions. Now, I know we're not dealing with fluoroscopy, but fluoroscopy still uses X-ray radiation. The main difference is it's a constantly on beam when a foot pedal is pressed, but the radiation exposure rates are less because they use an image intensifier to intensify the image. But here's an excerpt from the applicable portion. As a rule of thumb, the exposure rate to personnel standing 3 feet from a patient would be about 1/1000th of the patient's exposure if no protective measures are used. Now, with that in mind, let's go back to our initial problem and compare the two and see where the solutions probably got their answer from. The problems you encounter without using a thumb rule: 1, there's no way to transition a 672 milliroentgen entrance skin exposure to the side of the body. You also need to take into account scatter from other sources, like secondary scatter from the table or tube housing leakage. You also need to take the scatter probability into account, which was that 80% we mentioned earlier. And then there's a change in X-ray energy that we need to take into account, which is the 75 keV. When it's scattered at 90 degrees, goes down to 65 keV. And also, scatter from the entire volume of the body needs to be taken into account, not just one location. Now, with all that in mind, here's our two solutions. So the first one, we use the 1/1000th rule from the AAPM 58 report. 1/1000th of the entrance skin exposure of 672 milliroentgen gives us 0.672 milliroentgen. Or instead, you can use entrance skin exposure times your R factor divided by your distance squared, which the R value was 1 times 10 to the minus 3 meters squared. And after substituting in your 672 milliroentgen, leaves you with 0.672 milliroentgen. So they're both just different versions of the same problem. So at this point, it's just a matter of which thumb rule you want to remember for this problem going into the CHP exam. Part E asks us to provide 3 design features of the room containing the control panel that are required to minimize the technologist's dose. So 1, you ensure the distance between the patient table and the control room console is as large as possible. So this requires you to balance technologist safety or the ALAR concept, but also patient safety, keeping your eyes on the patient. 2, provide shielding between the control panel and the X-ray source. This should be accomplished during the design phase of X-ray room shielding using NCRP 147. And the viewing glass where you watch the patient, you want to make as thick as possible and or include leaded glass. So this is, I think, the least important because typically when the technologist is actually pushing the button, he doesn't have to have his eyes physically on the patient. He can move back behind the wall, push the button for the 100 milliseconds of exposure, and then look back in and make sure the patient's doing okay. Part F asks us specifically about mammogram procedures in a large hospital department. So one of the months, a technologist's monthly whole body dosimeter came back 80 millirem. And they ask, is this dose equivalent typical of an average monthly exposure? And explain the answer. So no, these exposure results are not what you would expect. Mammography examinations use low exposure techniques, which are low energy photons because the anatomy of the breast is small thickness and low density. Breast tissue is not very dense. These low energy photons are easily shielded, which is typically accomplished when the technologists stand behind a lead glass at the control console, and that console is on the other side of the room, usually in opposite corners of the room. So the first action of the radiation safety officer would be to compare the worker's results to other mammographers' dosimetry, posted dosimetry, or past results. Part G asks us to identify 3 design characteristics of an X-ray system or the associated image receptor that are required to minimize patient dose. So 1, all X-ray tube heads have a collimator, and that makes sure the useful beam is only analyzing the anatomical area of interest. So if you want to image the chest, you collimate that X-ray beam down to the chest so you're not exposing the neck or the abdomen. 2 X-ray tubes have a required amount of inherent filtration to remove low-energy photons. Low-energy photons do not have any medical significance whatsoever because they're absorbed by the skin. Those photons can't go on to interact with the body. They can't reach the image receptor. So these photons do not provide any diagnostic information. They only increase the entrance skin exposure. 3, optimizing screen film speed. It ensures the correct sensitivity of the phosphor. Therefore, less X-ray radiation is required to produce the optimal optical density. And number 4, while it's not required by regulation, the use of automatic exposure rate control will terminate at the optimal signal-to-noise ratio. This will optimize the image quality as well as the patient dose. It is an all-new installed X-ray systems, and its use is industry standard. Before we move on to the case study, let's talk about half-value layer and beam quality a little bit. So, beam filtration modifies the quantity and quality of the X-ray beam by removing those low-energy photons that I just talked about. Low-energy photons are attenuated by the skin and they don't reach the anatomical area of interest. 21 CFR 1020, which covers the requirements for diagnostic imaging machines, requires manufacturers to comply with minimum half-value layer requirements as a dose savings measure. So by adding progressive filtration to the X-ray tube outputs, not only do you have a number of photons reduced, but you also have the average energy of the photons being increased. The last half of this presentation is a case study that I did on board the USS Blue Ridge. So let's get started. The U.S. Navy Hospital Yokosuka Radiation Safety Office has quite the area of responsibility. Not only do we cover all the Navy assets in mainland Japan, but we also cover South Korea, Singapore, and Diego Garcia. We do all the medical physics testing and also cover dosimetry services for both medical and industrial radiography. During the time in question, the USS Blue Ridge, which is ported in Yokosuka, Japan, was out to sea where their medical x-ray room had a fault and they had to pull into Hokkaido, Japan for a normal port visit where I flew out to meet them and investigated the situation. The USS Blue Ridge, or LCC-19, is an amphibious command ship. It's the 7th Fleet's flagship and it's the oldest operational ship in the U.S. Navy. Its job is to provide command, control, communications, and computers and intelligence support to the command and staff of the U.S. 7th Fleet. The ship basically has some awesome port visits, which, in the right picture, they're pulled into Hokkaido, Japan, right smack in the middle of the Sapporo Snow Festival. Here's our scenario. An order was placed for a female patient for a routine anterior-posterior cervical spine diagnostic imaging study. The image was acquired using automatic exposure control, but the image was markedly overexposed. The X-ray tech confirmed the settings and a second image was obtained with the same results. After 2 failed exams, the image acquisition was secured and electrical power to the unit was terminated. At this time, the inspection of the X-ray unit, it was noted that the right side of the X-ray tube head had damage. They also looked at the films and it was noted that the exposure time was noted to be 155 and 152 milliseconds, which a typical exposure would have been about 10 milliseconds. So the senior medical officer notified the U.S. Naval Hospital Yokosuka Radiation Safety Officer, who flew to Otaro, Japan and Hokkaido to investigate. What you can see first on the screen is an optimal APC spine exam. This is what the technologist was hoping to capture when using the automatic exposure control. What actually happened was the next image, markedly overexposed, not what he wanted. At some point prior to the imaging study in question, the unit must not have been stowed for sea because the X-ray tech found the X-ray tube head in this condition on the screen, severe damage to the right side of the tube head. Additionally, when power to the X-ray unit is secured, the table bucky underneath the table moves freely. During testing, it was discovered that the table bucky's automatic exposure control system was no longer operational. It didn't work with individual or any of the detectors. Didn't matter what the combination was. So it's most likely that these heavy sea states caused the table bucky to slide back and forth, and when it crashed, it somehow damaged the AEC system. Now, what does the automatic exposure control system do? Well, it has some photo timers that are built into the bucky that holds the image receptor, and it records a signal to noise setting. Like, it captures the signal to noise ratio, and then it compares it to a reference voltage. The reference voltage is determined by the thickness of the patient that you can select on the control console. So if you have a thick patient, you would have a high signal to noise ratio. If you have a very small patient, you might set a very low reference voltage. So the comparator then compares those two and sends a signal to terminate at the exact time when you have the optimal image. So somewhere in these settings, or in this circuitry, the AEC is no longer functioning properly. So my task on board the Blue Ridge was to perform a patient exposure estimate and do a risk assessment, and then also do a full equipment survey to determine its safety to operate. The diagnostic exam taken was an AP C-spine exam. Would typically require 5 mass, which at a 500 MA programmed into automatic exposure control would terminate at approximately 10 milliseconds. Now, with the 2 attempts listed on the screen, the first exam instead terminated at 152 milliseconds, with the second exam terminating at 155 milliseconds. So these both attempts are executed before the technologist and the senior medical officer made the decision to secure from the procedure. On the right, we see an excerpt from Bone Tracker, which is the manual that technologists use as a reference for setting up exams, and we'll just note on that the SID is 40 inches to 44 inches, and a 15-degree angle looking at the cervical spine is used. We'll reference that in a minute. To reproduce the radiation exposure to the patient, I use the same technique factors that the X-ray technologist used on the patient from the previous 2 imaging studies, 75 kbp and 500 MA. I also used 160 milliseconds because when you're in manual mode, you can't select down to the individual millisecond. 160 milliseconds was the closest I could get on the control console, which equals 80 mass. I set the SID to 100 centimeters. We measured the patient's thickness of her neck to be 12 centimeters. And I determined on the next slides the source to detector distance and source to skin distance to be 60.66 and 79.29 centimeters respectively. So at a manual technique of 75 kVp and 80 mass, I measured with the detector 1059 milliroentgen, which when we convert using the inverse square law came out to be 620 milliroentgens. So what we're going to do in the next slide is go over how I took the measured and converted it to a calculated exposure to the patient. Let's go over one thing that you need to take into account when you're setting up this technique for the patient. Setting the machine to 100 centimeters perpendicular to the table is fine. But remember, from Brauntrager's manual, it said that it was a 15-degree rotation, which means we needed to rotate the tube head so that we see 15 degrees on the digital indication. Well, when we did that, it changes the SID to 103 centimeters because it automatically compensates for where it knows the table bucky should be in relation to the table bucky underneath the table. So what you need to do after that is lower the tube head perpendicular to the table so that you then correct to 100 centimeters SID. It's important to understand that the digital indication on the tube head is the hypotenuse of the triangle, not the perpendicular straight line of the triangle, the right side of the triangle. Remember, we said that the SID of 100 centimeters is the hypotenuse of this triangle. That's because the X-ray tube head is pointed 15 degrees to the right, which is where your image receptor is located. Now, I know that the bucky depth below the table is 8 centimeters. That's from the technical manual. The detector height is 30 centimeters, and the tube head angle, as indicated on the digital indication, is 15 degrees. So, to get the source to detector distance, we need to subtract the distance of the smaller triangle on the screen from the source to image distance. So to determine the right angle, the right side, the perpendicular length of that triangle, it's 8 centimeters of the bucky depth plus the detector height above the table, which is 30 centimeters, divided by the cosine of 15 degrees. When doing that, we get 60.66 centimeters source to detector distance. This calculation is almost exactly the same as the previous one. We know that the SID is 100 centimeters. It's the same triangle. The bucky depth below the table remains the same at 8 centimeters. However, P, the patient's neck thickness, is 12 centimeters. This isn't circumference, it's just thickness. And the tube head angle is also the same at 15 degrees. So to find the source to skin distance, we need to subtract the hypotenuse of the smaller triangle from our source to image distance. So the right side, perpendicular side of that triangle is 8 centimeter bucky depth plus 12 centimeter patient neck thickness. So 100 centimeters source to image distance minus 20 centimeters divided by the cosine of 15 degrees gives us 79.29 centimeters source to skin distance. Now the value we recorded on that radiation detector, I already told you, 1059 milliroentgen or 1.059 Roentgen. So to get from the detector to the source to skin distance, we need to use the inverse square law, just like we did from our CHP practice problem in the first half of this presentation. So we rearrange our inverse square law so that we're solving for the entrant skin exposure, which equals the exposure at the meter times the source to detector distance divided by the source to skin distance squared. So 1.059 Roentgen times those values squared equals 0.620 Roentgens per exam. Now we did 2 exams, so I multiplied it by 2, which equals 1.240 Roentgen. Now note, I didn't convert between mass values like I did in the practice problem, because that would, in my opinion, that would have been, this is just a little more conservative and it prevents downscaling the radiation.
Here's a refresher on the conversion from Roentgen to rad. All the information on the left is need-to-know information that you should know going into the CHP exam anyway. It may or may not be on the page that they give you in the exam sheet, but for ease of reference, it's good to just commit it to memory. So to start off, we have 1 Roentgen equals 2.58 times 10 to the minus 4th coulombs per kilogram. We also know that 1 ion pair equals 1.6 times 10 to the minus 19th coulombs. And in air, 1 ion pair has the ionization potential of 33.97 electron volts. Also, 1 electron volt is equal to 1.6 times 10 to the minus 19th joules, and 1 gray equals 1 joule per kilogram. So, combining all those together and removing our units that have canceled out, we've just proven that 1 Roentgen equals 0.00877 gray in air. If we have that exposure in Roentgens that we want to convert to a dose in rads, we'll first start by using the value we just calculated, 0.00877 grays in air per Roentgen. We can easily take that further by just converting grays to rads by multiplying by 100. But then we need to convert from a dose in air to a dose in tissue, and that's done by analyzing the mass energy absorption coefficients, which is what this next group of units looks like. So how do we determine this value? Now you may be accustomed to a typical value of 0.95 rads per Roentgen. Many textbooks will list this value because above 600 keV, the ratio of the mass energy absorption coefficients is relatively constant. But let's take a look at this to see how we get to that 0.95 rad per Roentgen, and then we'll adjust it for the energies we're concerned with to see how it'll play out differently. So the chart on the right is a value of the mass energy absorption coefficients for various energy ranges. Let's take 600 keV to 10,000 keV or 10 MeV. We'll take a look at the air mass energy absorption coefficients, and then we'll select the compact bone and muscle mass energy absorption coefficients. I take all of those values and put them into Excel. And to get the tissue mass energy absorption coefficient, I just take the average of the bone and muscle. So I have the average bone and muscle divided by air mass energy absorption coefficient on the right column, and then I average all of those out, and we see that the ratios average out to 1.084. Now we can return to that equation we had before. We didn't know how to determine that sum of all the mass energy absorption coefficients. But now we can carry the equation one step further and insert that 1.084 into the equation, and multiplying all of those values together, doing our unit analysis, we're left with 0.95 rads in tissue per Rankine. Moving on to calculating our actual ratio that we need for our diagnostic exam, we take the energies from 0.01 MeV, or 10 keV is the lowest this will go, all the way up to 80 keV, which is about 75 keV for our maximum energy spectra of our Bremsstrahlung radiation. We take the mass energy absorption coefficients from air and then compact bone and muscle. I take all of those values and put them into the Excel spreadsheet. Same method as before, I take the average of bone and muscle to determine my tissue mass energy absorption coefficient, divide it by the air, and average all of those values out, and I'm left with an average value of 2.325. Returning to the same equation from before, we're able to substitute in our ratio of the mass energy absorption coefficients. So moving forward, we have 2.325 tissue to air, and we multiply all those values together, do our unit analysis, we're left with 2.04 rads in tissue per Rankine. One step closer to calculating our effective dose, first we need to calculate the absorbed dose, which is in the units of rad or gray. It's the measure of the actual energy that's deposited in matter by the ionizing radiation per unit mass. So the unit mass could be air, it could be body, it could be anything that absorbs radiation. It's useful in determining expected deterministic effects from acute exposure. We had a exposure of 1.24 Rankine and our rad to Rankine conversion of 2.04, which leaves us 2.53 rad. So looking at the bottom left excerpt from a WHO article on fluoroscopy effects of acute exposure from high levels of fluoroscopy during interventional procedures, the typical threshold absorbed dose for early and transient erythema, which is the lowest effect of skin that you'll see, is 2 gray. So 2.53 rad is approximately 1.3% of that level, which is about 200 rad or 2 gray. So the patient will not see any reddening of the skin. The absorbed dose we just calculated is used in calculating the equivalent dose. It has the units of rem or sievert, and it's used to represent the stochastic health effects of ionizing radiation to an area and the probability of any radiation-induced cancer or genetic effects. What it does is it takes into account the different strengths of the various forms of ionizing radiation, like photons, protons, or alpha particles. And we then use it to calculate an effective dose. So the bottom left has an excerpt from ICRP 103. So looking at this, let's remember that we're in a diagnostic X-ray exam. So we are concerned about photons. But photons interact via photointeraction and go on to produce electrons. So if you read ICRP 103, it makes note that the photon has the radiation weighting factor of 1, and it actually includes the electrons that are produced as a result, which also have a radiation weighting factor of 1. So all we are concerned about is a 1 rem per rad radiation weighting factor. So our equivalent dose is equal to the sum of our various ionizing radiations times our absorbed dose, and we substitute in 1 rem per rad times our 2.53 rads, which is equal to 2.53 rem. We'll close out our calculations by looking at the effective dose, the final value we're looking for, which has the same units of rem and sievert, same as the equivalent dose. The only difference between effective dose and equivalent dose is it takes a partial body exposure and changes it so that it looks as if it were a whole body exposure to give a realistic cancer risk to the whole body. It's useful in risk comparisons, which was what we're going for when we wanted to talk to our patient that was overexposed on the ship. The bottom left has the tissue weighting factors from ICRP 103, and the ones we are concerned about is the tissue weighting factor for the skin, the tissue weighting factor for the esophagus, and also the thyroid. So the effective dose is equal to the sum of all of the products of the tissue weighting factor and the equivalent doses to those areas of the body. So the tissue weighting factor of the skin times that equivalent dose, tissue weighting factor of the esophagus times that equivalent dose, and the tissue weighting factor of the thyroid times that same equivalent dose. So we substitute in our values, and we're left with 0.228 rem or 228 millirem. We can do a cancer risk comparison by using our effective dose. On the screen is a chart or table graphic I pulled from the Environmental Protection Agency's website. The values themselves are derived from NCRP 160. Coincidentally enough, the 228 millirem is actually identical to the amount of radon in an average U.S. home. So that's pretty relatable to the patient who doesn't have any regular dealings with radiation. You can easily explain it to him or her that what you just experienced with this x-ray tube is what you would get from just living in Colorado, for example. Or if the patient's had a CT before, you could say, well, 200 millirem is one single head CT, and you got just a little bit over that with 228. We don't expect any adverse effects from CT. We use them in treatment to diagnose disease, and we treat millions, tens of millions of patients in the U.S. every year using this modality, so no concerns there. So this is one method to put him or her at ease.
This is a useful chart graphic produced by the Department of Energy. It's called the dose ranges chart. You can find it in REM or sieverts, but because I did the calculation in REM, that's the one I decided to use on the screen. Starting in the bottom right, it has a couple useful conversion factors, and it talks about the lethal dose, and then it goes above and talks about some medical diagnostic exams, what absorbed dose you would get from those exams. And then starting at the top, note that it says dose ranges. So that means it has all of the ranges in a logarithmic scale. So it goes 0 to 10,000, 0 to 1,000, 0 to 100, 10 rem, 1,000 millirem, 100 millirem, et cetera, et cetera. So the top two are what you would see, where you would see acute radiation effects. So erythema, acute radiation sickness, GI syndrome. The next one I didn't find too important to go over in this discussion. The next one is important because that shows where the occupational exposure limit falls for a worker that's working with ionizing radiation by regulation with the Nuclear Regulatory Commission. The next one below that is actually where our patient's radiation exposure falls. And then the bottom one is where it talks about very, very low background and what the limit is for the public from ionizing radiation sources in the workplace. So you can see with the red arrow where the patient's radiation exposure fell from this exam, and it's well below the acute radiation effects that you would see at the top two dose ranges.
Thanks very much for listening today. I hope you enjoyed it. This should be posted to Mill Suite, specifically Mill Tube, so if you have any comments, you can leave them there. I'm looking forward to doing some other topics, and if you have any recommendations or want to participate in one yourself, please comment below or contact me. My contact information should be in the description. Thank you.